As we said, this is nitrogen triiodide, very, very sensitive contact explosive. Decomposition reaction, releasing iodine and nitrogen. Iodine is the big cloud. Now this is fun, but this is even more fun. Remember, we have another exam coming up. Yes. At the end of Chapter 5, we're scheduled for our second exam. Now, according to the syllabus, this was supposed to be next Wednesday, and then the Friday before spring break, we would start Chapter 6. Instead of that, I decided to simplify things a little bit and move the exam to Friday, so that's the day before spring break. And we will keep quiz 2 as usual on Friday. Any questions? We will have lots of time to review this stuff. The lab on Wednesday. We have lab on Wednesday, right? Well, we don't have lab on Wednesday this time. It's nomenclature problem set or something like that. We've done that. So I will, what it is basically a sheet where you're supposed to look at it and write down names. We've done that. I will scan their sheet and put it on Blackboard, and everyone can do it. That's a fine thing to do. In order to get credit for the lab, what we'll do is there will also be a link on Blackboard. If you have not done the 3 nomenclature tutorials from Chapter 3, do them, send emails, that's good, and then click yes. That's all you have to do for that lab. If you haven't done them, if you haven't finished them all, go back and do them, whatever. Remember, exam will be Chapter 4 and 5. So mole concept and reactions. All right, we talked about chemical reactions. This is an example of a very simple chemical reaction. We read something like this: 2 aluminums, 3 bromines, 2 aluminum bromides. Put it in the context of the mole concept. We can also say we have 2 moles of aluminum, 3 moles of bromine, giving us 2 moles of aluminum bromide. In Chapter 6, we will do stoichiometry. Stoichiometry basically just puts this into more of a problem format. For example, I just said 2 moles, 3 moles, 2 moles, right? All of Chapter 6 comes down to something like this. What if we only had 1 mole of aluminum? How many moles of product would we get? 1. Right? How many moles of bromine would it take? Not 3, 1.5. So that's the basic concept of stoichiometry. Remember, we can also express this in terms of mass. Put our molar mass here. This is 2 times whatever aluminum is. That makes it about 54 grams. Reacts with 3 moles of bromine, 479 grams, to give our product. Conservation of mass says the mass on this side must equal the mass on this side. Very simple concept. All right, we looked at balancing equations, and we practiced all weekend. Sticking coefficients in. Let's go ahead and look at some simple examples. Go ahead and balance these guys. At the end of class today, well, actually, as of right now, on Blackboard is the balancing equation quiz, 10 points. Um, you have 2 attempts, I believe. Very simple quiz. Just go in and enter your coefficients. On Blackboard, remember you must enter 1 if the coefficient is 1. Otherwise, you will not get credit. All right, for this guy, I look here, I have 3 hydrogens, that's an odd number, and I have an even number on this side. I probably want to double this. That will give me 2 ammonias on this side, right? 2 nitrogens. So we're going to need a 2 in front of this guy. That means we also need 2 sodiums. So let's see, if we have 2 of these, that's 6 hydrogens. 2 of these, that's 4 hydrogens. We only need 1 H2 to make it work. For our next one, we also have an odd even here in terms of our oxygens. We have 3 oxygens on one side, and we have 4 on the other. Probably I would start off by doubling this. That gives me a total of 6 oxygens, right? I also need to double the SO2 because I now have 2 sulfurs here. So I put a 2 here. That'll give me 4 oxygens. This is 6, we just said. All we need is these 2, and I think it balances. And finally, in our last one, well, we have an odd number of oxygens here. We have 1 here, so that's even for the whole side. And we have an odd number here. If we double this guy, that'll give us an even. That gives us 6 oxygens. Well, we happen to have 5, 6 on this side. That's good. So we've doubled this. That's H2. We have H2. 2 nitrogens. 2 nitrogens. And I think that's all you have to do. Any questions on the concept?
So, the best idea when you start is looking either oxygen or hydrogen, then it's like the even number or odd number.
You know, that's the way I do it. There are lots and lots of ways to balance equations, but I think that that's just the simplest. Obviously, it's not going to balance if you have odd numbers on one side, even on the other. The only real exception to that rule is if you have something on, say, this side or this side, it's a big molecule, say with 6 carbons or whatever. You know, then take care of the 6 carbons first, and then work with something else.
Because when I look at the internet, they said like leave oxygen hydrogen last and one with oxygen. So I'm just trying.
Everybody's got the wrong way to do it. I think the even and odd is the simplest and the fastest. I mean, there are algorithms. There's an equation that you can write out to do this. But who wants to do that? All right, we talked about types of chemical reactions. Reviewing here, we had synthesis reactions. We said we could do this from elements or compounds. Basically, the hallmark of a synthesis is we start off with 2 or more things, and we wind up with something new. Typically, we'll have 2 or 3 things on this side and 1 thing on this side. That's typical, that's not required. Decomposition, we go backwards. We start off with something, typically 1 thing on this side, and we're going to break down into something else. Here we're going from a compound to elements, compound to compound. You could go from a compound to elements plus a compound. Same sort of thing, um, pretty much just the opposite of our synthesis reaction. We talked about replacement reactions. We have single and we have double. In a single replacement, we're going to take an element and a compound. We're going to let those react, and we will get an element and a compound. Typically, the nonmetal will replace the nonmetal in the compound. If we have a metal as our element, it would replace the metal in the compound. We remember that there are two very important exceptions in these types of reaction. Hydrogen and carbon act as if they are metals. Just remember that. Hydrogen and carbon act as if they are metals. Double replacement of ions. Here we're taking two compounds, typically in aqueous solution. They will react so that they simply swap ions. Silver here will pair with chlorine, sodium will pair with nitrate. In order for any chemistry to happen here, you must either make a solid on this side of the equation, that's precipitate is called, or a gas. Otherwise, the ions just sit there in solution, bounce around merrily, and no chemistry occurs. Any questions? Oxidation and reduction. Well, this is the class that we're going to go over today. In a redox reaction, the oxidation numbers of the compounds change as the reaction occurs. This is probably the most important of and the broadest of these reactions that we'll talk about. And we'll see examples of almost all other types that are actually redox reactions. For example, we said oxidation numbers were such that we're going to compare the element or the compound with that element as it occurs in the periodic table. Here we have carbon and oxygen. They're both elements on the periodic table, so there's no difference. So by definition, their oxidation numbers are 0. Now we'll go over a set of rules today. But the rules that we know so far basically tell us that oxygen is typically going to be -2. If oxygen is typically -2, that means in carbon dioxide, we have 4 negatives here. In order for this to be neutral, the oxidation number of carbon must be +4. So our oxidation numbers have changed. 0 to +4, 0 to -2. That's a redox reaction. All right, we'll do more on that in a minute. We talked about solubilities. Let's just make sure we can do this. Look at these reactions. These are all double replacement reactions. Go ahead and write the products, balance the equations, and of course tell me if an insoluble product is formed. All right, our first one. Our insoluble compound. We're going to swap our ions. We're going to make magnesium nitrate and silver chloride. We remember that silver chloride is our very classic insoluble compound. Okay? In order to balance this, silver is +1. We have 2 chlorines. We're going to need 2 silver nitrates. Magnesium is +2. Nitrate is -1. We already said we had 2 of these guys. I believe that this is the balanced equation. And our second one, sodium is going to pair with nitrate. Barium is going to pair with sulfate. Sulfate's -2, barium is +2. Barium sulfate is another one of our classic insoluble compounds. Yeah?
Why did you have to put the 2 for the top one? Couldn't you just like switch?
Well, we have 2 chlorines. So we need 2 silvers, AgCl. Has to be the same numbers and types on both sides. This also gives us 2 nitrates here. And remember, we need 2 nitrates for our magnesium. All right, so we have barium, we have sulfate, we have 2 sodiums, and we have 2 nitrates. Barium sulfate is our insoluble compound. I don't think we need coefficients at all. Well, we have 2 sodium nitrates. That's not really balancing, that's just keeping track. And finally, here we have sodium sulfide reacting with lead nitrate. Now our ions here would be sodium nitrate, we know that's soluble, and lead sulfide. We don't have a clue about sulfide, do we? What if that was oxide or hydroxide? We do have a rule. And the rule is that virtually all hydroxides and oxides are going to be insoluble, unless they are governed by the first rule, which is period 1 and ammonium. Turns out, if you look at your periodic table, the sulfur lives here right underneath oxygen. Sulfur is an oxygen wannabe. Okay? Whatever oxygen does, sulfur tries its best to do. Therefore, just like oxide would be insoluble, lead sulfide is also insoluble. Any questions? If it's not governed by rule number 1, which again is first period, group 1, not period, group 1 and ammonium. They're always soluble. All right. Let's do a couple quick predictions. What I'd like you to do here is to predict the product of these reactions and write a balanced chemical equation. Well, we know that we're dealing with 2 nonmetals here, so we're going to make a molecular compound. Nitrogen has 5 valence electrons. It tends to bond to 3 things to give it 8. Probably we're going to be making ammonia, NH3. If we're making ammonia, NH3, then we have an odd number of hydrogens on this side and an even number on this side. So let's do our standard thing. We will double our ammonias, so we have 2 ammonias. That's good because we have 2 nitrogens, don't we? If we have 6 total hydrogens, we need 3 H2s. Zinc plus HCl. You can think about this as a single replacement reaction. And remember we said that hydrogen and carbon acted funny. They act like they're metals. So we're starting off with an element and a compound. We expect to get an element and a compound. Now, hydrogen is going to pretend it's a metal, that it's going to be the element, right? And zinc will be in the compound. Hydrogen as an element is going to be H2. As our compound, zinc is going to pair up with chlorine. Now zinc is a group 2 metal. It will form. It's not group 2. It's a transition metal, isn't it? But it's almost always plus 2. It will form zinc chloride, ZnCl2. Let's see, we need to make H2, so we need 2 of these. That gives us 2 chlorines to pair with our zinc. I think that's all we have to do. Once again, hydrogen pretending it's a metal will be replaced by the metal, zinc. So hydrogen winds up the element, zinc winds up in the compound. Silver nitrate and magnesium chloride. Well, this is a double replacement reaction. Silver is going to pair with chlorine to make silver chloride, which is insoluble. So once again, we have 2 chlorides. This is going to be AgCl, so we need 2 silvers. Once again, magnesium is plus 2, each nitrate is minus 1. Simply go and exchange them. And that's what we get. Now finally, here we have iron 3 oxide reacting with chlorine. This is going to be a single replacement, isn't it? The nonmetal chlorine is going to replace the nonmetal oxygen. So we will get iron 3 chloride. And we will get Oxygen is our element. So we're going to exchange chlorine and oxygen. Let's see. Iron 3 chloride. Chloride is -1. We have 2 irons. So that means we need 6 total chlorines, right? We have 3 oxygens here. This is 6, so we've doubled our iron 3 oxide. We have doubled our 2 moles of iron 3 chloride. If you look at this reaction, the reason that we had to double everything as we go across here is our first time through, if we had simply taken this and got 2 of these guys, we would have 3 oxygens, and this is the only place oxygen shows up, and it comes in pairs. So we have to double that in order to make O2, and then go on. So a simple single replacement reaction, non-metal replacing non-metal. There's one other bit of nomenclature that you will encounter here and there. Some plants, some books, whatever, lots of people actually, like to use what are called net ionic equations. If you've noticed when we've done a double replacement reaction, we start off in solution, in this guy, with silver ions, nitrate ions, potassium ions, and chromate ions. Now, chromate is the one that we learned, but that's insoluble. I'll just tell you that. But when we're left, we have the silver chromate on the bottom of our tube, and we still have potassium ions and nitrates. Well, they come from here, don't they? Nothing happens to those, they're still bouncing around in the beaker. So, the idea of a net ionic equation is that you don't really care that there's potassium nitrate there. Doesn't do anything, doesn't react, doesn't change. So all you do is you put down the ions that actually react. Now on your exam, we're not going to do this, but you probably will see this as you read books and whatever. These are called spectator ions, potassium and nitrate. They're just hanging around doing nothing, only bother putting down the ones that do the reaction. So just a bit of nomenclature so you're up to date on it. Any question on what we talked about last time? All right, let's go and do redox. As we've said, in a redox reaction, the oxidation number of the elements can change. We're going to have 2 ways that this will happen. The oxidation number will increase, or the oxidation number will decrease. If the oxidation number increases, we call that oxidation. If the oxidation number decreases, we call that reduction. Now there's a simpler way that I remember, as I always get confused too, and that is just to remember the phrase, oxidation is loss of electrons. Worth writing down somewhere. Oxidation is the loss of electrons. Let's say we had something that was 0, an element, and it went to +4. In order to go to +4, it has to lose electrons, doesn't it? 4 of them. That is an oxidation. If you went from +4 to 0, you would add electrons back, and that's reduction. But you only have to remember one of them. As we said, the oxidation number starts off with the element in its standard state, sometimes called the ground state. This is just the stuff as you find it on the periodic table. Copper metal, carbon as an element, oxygen, nitrogen, etc., just as they are in their standard state, not in a compound. So we're going to compare the element in the compound with the element in our periodic table. That's all we do. We decide if it has more electrons than it does here, or fewer electrons, and that'll make it plus or minus. We talked about simple binary ionics for magnesium bromide. What we said simply was that the oxidation number was going to be the same as the charge. So in magnesium bromide, magnesium is group 2, it's a +2 cation. Bromine is group 7, it's a -1 anion. So if we put this in terms of oxidation numbers, magnesium is +2, bromine is -1. In the periodic table, bromine has 7 electrons. Here it has 8. That's a -1. In the periodic table, magnesium has 2 electrons in its valence shell. Here it has 2 fewer. So it's a +2. Lithium phosphide, group 1, +1 ion. Phosphorus, group 5, -3 ion. Oxidation number, lithium is +1. Phosphorus is -3. So for these guys, it's really simple. It's just the charges. Now for a molecular compound, I showed you this set back in chapter 2 or 3 or something. We have rules for assigning oxidation numbers. These rules appear in an order. And they're in this order because you start at the top and work your way down. If the rule is up here somewhere, it wins. Pure elements are 0, same as they are on the periodic table. Group 1 and Group 2 are always 1 and 2. Just their ionic charges. Fluorine. Fluorine is our most electronegative. It will always grab the electrons, and it will always be a -1. All right, so those 3 are really simple. Now we start with the ifs and whatevers. Hydrogen. If hydrogen can bond to both metals and nonmetals, okay? If it bonds to a metal, any metal, it will be -1. If it binds to a nonmetal, it will be +1. Metal, -1, nonmetal, +1. Oxygen, as we've said, is almost always -2. Now we'll see that today we will see examples where it's not. But that's because one of the rules up top here takes precedence. Halogens are almost always -1 unless they are bonded to oxygen. Unless they are bonded to oxygen. Sulfur and selenium are going to be -2, just like oxygen, except if they happen to be bonded to oxygen, and then oxygen takes charge. Now, none of us like having to remember rules. On the exam, you do get another 3x5 card, that's fine. But I wouldn't waste it writing these things down. We'll see that these rules are actually very simple. Let's show just how simple they are. What's the oxidation number for each element in sulfur trioxide? Well, sulfur was way down on the very bottom list, right? Oxygen was above it. Oxygen is going to be -2. Now, sulfur trioxide is a neutral molecule, isn't it? If each oxygen is worth -2, how many negatives do we have? 6 of them. That means that for this to be neutral, sulfur must be +6. 6 negatives, 6 positives. Everyone get that? Let's do nitric acid. Now we remember that hydrogen was way up there on our list. It was above oxygen, wasn't it? Hydrogen is going to be bonded to our oxygen. So that makes it, well, that will make it +1. But let's start off with our oxygen here. Once again, we have 3 of them, and they're -2 each. Now, nitric acid. Hydrogen is bonded to the oxygen. It's a nonmetal. So that means that hydrogen will be +1. So now let's just add up what we've got. We have 6 negatives, 1 positive, right? The whole thing is neutral. That means hydrogen or nitrogen must be +5. Six negatives, 6 positives. Hydrogen sulfite. Well, our oxygens here are going to be -2, aren't they? Our hydrogen is going to be bonded to a nonmetal. Both sulfur and oxygen are nonmetals, so got to be bonded somewhere, right? Therefore, it's going to be a +1. Actually, in hydrogen sulfite, the hydrogen can be bonded to either the oxygen or the sulfur. But that doesn't matter because they're both nonmetals. So, hydrogen is going to be +1. Now, we have 6 negatives here, don't we? We have 1 positive. But the whole thing is negative, right? So that means really we have 6, 7 negatives and only 1 positive. In order for this to wind up with a net negative charge, we need our 6 negatives here and only 5 positives here. So we must have 1 negative charge left over. All right, let's see how this, well actually, the exam has both. You will have a question like this, and you will have questions like this. Very quickly, take each of these and give me the oxidation number for each of the elements. My goodness, I must have left my coffee in the car. Oh, another reason to cancel class. All right, look at. Sorry. Look at potassium permanganate. Our oxygens are going to be -2, aren't they? So that's 8 negatives. Remember, we had a rule for group 1 elements. They were always going to be +1. So we have 8 negatives. We have 1 positive. Manganese must be a +7. Each oxygen is -2. Potassium must be +1. Therefore, the manganese must be +7. 8 positives, 8 negatives. Barium sulfide. Barium is group 2. It will have a +2. Every oxygen is -2. That's 6 negatives, right? So we have 6 negatives, 2 positives. What's our sulfur? +4. Aluminum, a group 3 metal, this will be +3. Okay, no problem. Let's look at our chlorate. Inside of our chlorate, the oxygens are going to be -2, aren't they? So that's a total of 6 negatives. But, we don't have to worry about ×3. We have 6 negatives. And chlorate itself is -1. So that means we have to have 1 negative left over. So for our oxygens inside of our parentheses here, if these guys, this is -6, the whole thing is -1, chlorine must be 5. Now think about this again. inside of our parenthesis. Each oxygen is -2. That's 6 negatives. In order for chlorate to be -1, chlorine must be +5. Now we happen to have 3 of them to balance out the aluminum, but we don't care about that in terms of oxidation. Silver nitrate, we know silver is going to be +1 because it always is. Nitrate is -1. We have 6 negatives here, don't we? If we have 6 negatives, how many positives do we need so that we have 1 negative left over? It's got to be 5. Yeah,
Why do you need the one negative for both?
because nitrate in O3 is -1 charge. That means you must have 1 extra negative charge. And finally, the ringer here, barium cyanide. Well, barium, a group 2 metal, it will be +2. And how about this cyanide? Well, in our whole list of rules, we had nothing at all about carbon or nitrogen, did we? Well, the answer is carbon is +2, nitrogen is -3. But how did I know that? If you have something that's not governed by our rule, what you do is you just look at the Lewis structure. This is cyanide anion. Okay? Now, these covalent bonds, the electrons in the covalent bonds, are going to belong to the element that is most electronegative. Remember electronegativity. There it is. Remember, we start down here with little numbers. We wind up here with big numbers. Nitrogen. I can't read it. Looks like it's about 3 something. Carbon is 2.6 something. Nitrogen wins. That means that all of the electrons in this covalent bond belong to nitrogen. So it gets all of them. Now, let's compare this, what we have, to our periodic table. Nitrogen is a group 5 element. How many electrons does it have now? It has all those from the covalent bond. That's 2, 4, 6, plus 2 more, that's 8. Now that's 3 more than it has sitting here in the periodic table, which means it is -3. Carbon is group 4. All it's got here is 2. So it's missing 2 electrons. And that makes it +2. So if it's not covered by the rule, you look to see which one is most electronegative. You give them all the electrons, and then just compare what you've got to the periodic table. If these were the same, if they're both carbon or both nitrogen, then you would split them evenly. But if they're not the same, most electronegative element gets them. All right, tutorial number 1 here. What's the oxidation number of lead in lead nitrate? Remember, for simple ionic compounds, it's just the charge, isn't it? Nitrate is -1. That means lead must be +2. We have 2 nitrates, 1 lead. Lead must be +2. Now here's the rule. Remember, we've got to add up to 0. Let's look at our nitrate one more time. The tutorial doesn't make you do this, but what's the oxygen going to be in our nitrate? It'll be -2, won't it? Oxygen will be -2. Now nitrate, NO3 minus, right? We have 6 negatives. How many positives? Got to be 1 less, got to be 5. So the lead is 2, nitrogen is 5, oxygen is -2. How about pH 3? Now this is a molecular compound, isn't it? Phosphorus trihydride. What's our rule with hydrogen?
Last one.
It's bonded to a non-metal, right? So it will be +1. If it is +1, and there are 3 of them, phosphorus must be -3. Hydrogen is +1, phosphorus -3. Remember I was telling you about bankside cannons? How much fun they are? That's calcium carbide. How about carbon? There's no rule. No rule. So we have to do electronegativities. But here we have 2 carbons, they're bonded together, so they're the same, aren't they? So here's our Lewis structure. Looks like this. Because they're the same, we're going to split all the electrons. So this carbon now has 1, 2, 3, 4, 5. And so does the other carbon.
So you said before that hydrogen and carbon, they act like a metal?
Oh, that's for single replacement
Oh.
reactions, not oxidation numbers. So this carbon has 5 electrons sitting there in the periodic table. How many does it have? 4. It's group 4. Now it's got 5. Therefore, it must be -1. They're both -1. All right, now that we can do oxidation numbers, let's do redox reactions. Remember we said that oxidation with loss of electrons, an element which loses electrons is said to be oxidized. Reduction is a gain of electrons. An element which is reduced, it has a decrease in its oxidation number, that means it gains electrons. Now the words, some of these words get a little bit messy, but you have to remember oxidation, loss of electrons, reduction, gain of electrons. Let's look at this. Question 1, is this a redox reaction? And if it is, which element is oxidized, which element is reduced? Aluminum is an element, it's 0, isn't it? Iron's an element, it's 0, right? What's iron here? That's iron 3 oxide, so it's +3. Aluminum is an ion over here, or bonded with oxygen, is a +3 ion, isn't it? So the oxidation numbers have changed from 0 to +3, from +3 to 0. So yes, this is a redox reaction. Whereas 0 +3 -2, whereas 0 +3 and -2. Yes, it is redox. Which element has lost electrons? Aluminum has gone from +0 to +3. To do that, it has to lose electrons, doesn't it? Iron has gone from +3 to 0. To do that, it has to gain electrons. Aluminum has lost electrons, 0 to +3. Iron has gone from +3 to 0 and gained electrons. This has been oxidized. This has been reduced. Oxidation is the loss of electrons. There's one more bit of nomenclature that you will encounter, and that is oxidizing agent and reducing agent. Here, iron has been reduced, right? Well, somebody had to take the electrons off the aluminum, didn't they? That was the iron. Therefore, we say that since aluminum was oxidized, the guy that did it was the iron, and we call it an oxidizing agent. That's just the guy that did it. All right, this is a really neat reaction. This is called thermite. This is what we just balanced. Aluminum plus iron 3 oxide giving iron and aluminum oxide. Sounds like a harmless reaction, right? This is a little teeny flower pot. Flower pots, as you know, have a hole in the bottom for water, right? This is a big pot full of sand. In this little pot up top, we have a mixture of aluminum and iron 3 oxide. This mixture is actually called thermite. Now you will see a brave individual come running in and stuff a hot piece of burning magnesium into our thermite. And then run away. What's happening is our redox reaction is going. And as it is going, the molten iron that we're producing is dribbling out the hole in the bottom here into our bucket of sand. Now this used to be a really fun thing to do in the room. Everybody in the first 4 rows got burned. When you're done, you're in our bucket of sand. That's a bright molten chunk of iron. And when it finally cools, it looks a whole lot more like our chunk of iron. The thermite reaction. During the Second World War, they had thermite bombs. When they bombed cities, they dumped bombs of this stuff all over them. It was a terrible thing. All right, go ahead and look at these guys. Decide if they are redox. Assign oxidation numbers and decide who has been oxidized, who has been reduced. The key here is to look for elements. Elements are going to be 0, aren't they? Here we have a compound. So they're not 0 anymore, are they? So number 1, yes, it is a redox reaction. We have no idea what tantalum is, except it's 0 here. Bromine is going to be -1 though. That means our tantalum must be +5. 5 negatives, 5 positives. Who has lost electrons? The tantalum has gone from 0 to +5. It has been lost electrons. Therefore, it has been oxidized. Bromine has been reduced. See how simple that is? To our next one. Silicon's going to be 0. Aluminum's going to be 0. We know aluminum is +3 here. It's 0 there. If oxygen is -2, silicon must be +4. So, what element was oxidized? Which element lost electrons? Silicon started off as 0. It's now +4. It lost 4 electrons. How careless. No change in oxygen. Aluminum started at +3. It's now 0. It had to gain 3 electrons. Therefore, it has been reduced. Remember we said lead sulfide was a solid, right? Sulfide, just like oxide, going to be insoluble, and it's going to be a -2. Sodium is what? Group 1, got to be +1. What's it here? Still +1. Okay. Sulfur, -2. -2. What's our lead here? +2. What's the lead here? plus 2. Anything happen to our nitrate? Nope. No change in oxidation numbers. This is not a redox reaction. Something you can remember, when you have a double replacement, you will not have redox. Single replacement, yes. Double replacement, no. Hydrogen acting as if it's a metal, right? It's going to start off as 0, winds up as +1. Nickel starts off as +2, it winds up at 0. This is a redox reaction. Hydrogen has gone from 0 to +1. It lost an electron. It's been oxidized. Nickel has gone from +2 to 0. It gained 2 electrons, and it has been reduced. Tutorial. This is a redox reaction. Nothing has happened to the oxygen in our vanadium oxide, but what happened to the vanadium? Has it been oxidized or reduced? Now on the tutorial, you click a button on Blackboard, and you will see this on Blackboard. You have to write the word oxidized or reduced. Please spell it correctly. All right, look at our start here. We have VO +2. So vanadium oxide is +2. What's our oxygen going to be? What's the oxygen going to be? -2. Now, for the whole thing to wind up +2, how many positives do we have to have in there? 4. So our vanadium is +4. Here we have vanadium dioxide with a +1 charge. How many negatives do we have? 4 of them, right? If we have 4 negatives and we're still +1, how many positives? Gotta be 5. So our vanadium has gone from +4 to +5. Does that mean it gained electrons or lost them? It lost it. It lost an electron. It has been oxidized. Oh, the double arrow?
Yeah.
That's an equilibrium. We will briefly discuss equilibrium. In general chemistry, you should spend a full month talking about nothing but equilibrium. But here at Triton, they don't cover equilibrium much. Here we have thallium +4 going to thallium 0. Oxidation or reduction? Did it gain electrons or lose them? It has gained electrons. It is a reduction. Hello? +4 zero reduction. All right. We talked about synthesis reactions. Almost all synthesis reactions are going to be redox. In this guy, our tantalum is 0, bromine is 0. Here, bromine is -1. Tantalum must be +5. How about this guy? Phosphorus element, 0. Chlorine, 0. Chlorine is going to be -1. That means our phosphorus must be +5. Most synthesis reactions, probably not all, but most, are going to be redox. Decompositions are also going to be mostly redox. Mercury 2 oxide, right? Mercury is +2. Here is 0. Oxygen is 0. Oxygen here is -2. Mercury is +2. In the process of this reaction, which element is oxidized? Which element loses electrons? Oxygen, to go from -2 to 0, must lose 2 electrons, right? That's actually why they call it oxidation. Because oxygen is the primary oxidizing agent around. All right, let's look at this guy. Very quickly, everyone just try this one. Just write it down and put the numbers on it. You know that oxygen is going to be 0, right? Look at water. Oxygen here is going to be -2, right? Hydrogen's bonded to a nonmetal, so it's +1. How about hydrogen peroxide? If we did what we've been trained to do so far and say oxygen is -2, every hydrogen would have to be what? +2. It can't be. It's only got 1 electron. It can't be. That's why it's higher up on the list than oxygen is. Remember, hydrogen bonded to a nonmetal will be +1. Which means that our oxygen must be -1. Well, that's disturbing. Hydrogen is higher on the list. If it's bonded to a nonmetal, it will be +1. To be neutral, oxygen must be -1. Let's continue our disturbing behavior here. Barium react with oxygen. Synthesis reaction. To get barium oxide. Barium and oxygen are both elements that are 0. Barium is a group 2 metal, isn't it? By definition, it will be +2. That means that every oxygen must be -1. And let's do the real killer here. Potassium reacts with oxygen to give potassium oxide. Both of these are 0. What will the potassium be? Our second rule, it's group 1. It will be +1. Which means that every oxygen is what? -1/2. This is called a superoxide. These are peroxides. In a peroxide, oxygen is -1. In a superoxide, oxygen is -1/2. Let's just look at a couple more quickly. Hydrogenation reactions, once again, hydrogen acting as if it's a metal, going from 0 to +1. Single replacement, we've seen lots of these. Lead 2 going to lead 0, aluminum 0 going to aluminum 3. Remember, except for hydrogen and carbon, metals replace metals. This is a single replacement, isn't it? And we did something in lab that was very similar to this. We took a metal, reacted it with a salt, got a salt and a metal. We did iron and copper. Remember, copper nitrate. Classic example of a single replacement reaction. This guy is actually a very classic example of something that you very often do in lab. Problem is that the price of silver these days, they don't let students mess with it anymore, but it's a shame. In our beaker here, we have silver nitrate. Here comes a piece of copper wire. You set it in there, and it just sits. Nothing's happening. But if you wait a couple minutes, it starts to get fuzzy. And as it sits longer and longer and longer, it gets fuzzier and fuzzier and fuzzier. What's the fuzz? Silver metal. And also look at the solution. The solution is getting bluer and bluer as the copper grows more and more silver on it. Why is it blue? It's blue because most copper salts, just like copper nitrate, are brilliant blue crystalline salts. So we're making copper nitrate in our solution. It's blue. Silver is these little whiskers that grow. How do you know if something like this is going to happen? Well, it's called the activity series. Basically, any metal that's above will replace any metal that's below. What we did in lab was iron, right? And copper. Iron was our element. Copper was our compound. Iron replaced it. And we grew this little bit of copper on our shiny nail. Anything that's above it will replace anything below. Again, by example, for our silver, copper, silver is here, copper is there. Therefore, copper goes in solution, and silver rows like that. All right, let's just do 2 or 3 quick problems, old test questions. If we take aluminum and chlorine and react them, what is likely to be formed? Will the compound most likely be ionic? What do you think? Come on, it's a metal. Of course it'll be ionic. Oxidation number of aluminum in the reactants is 0. Is that true? It's an element. That's true. And the molecular formula, aluminum will form a +3 ion. Most likely be aluminum chloride. All of these are correct. Now,
When you say elements, do you mean like gas?
no, aluminum's an element, it's a metal.
Aren't they all elements?
Those are. Aluminum and chlorine. Chlorine is an element too. Its oxidation number at the start of the reaction is 0. The end of the reaction is -1. Aluminum goes from 0 to +3, which is
Like when it combined.
so the question is, in the reactants, was it 0? Sure, it's an element.
How do you know like when you say it's element? Because like you can look at oxidation number here when it's
No.
only Al.
Read the problem.
Yeah, but
Those
not
elements, aluminum and chlorine.
But
Which of the following is likely to be insoluble? Remember I told you there were 2 that were given that you never ever forgot. Silver chloride and what? Barium sulfate. I remember a cute little movie where we took 2 clear solutions and got this stuff falling out. That was lead iodide. In the reaction shown below, the oxidation number of fluorine does what? What is it here? It's a 0, isn't it? What is it here? Rule number 3, fluorine is always -1, right? So we've gone from 0 to -1. Changes from 0 to -4, that's silly. Does not change. -1 in the reactant, so it's 0. That's stupid. None of these are correct. Last one. On your exam, you'll have a problem very much like this, where you are asked to take a compound and simply tell me the oxidation number for every element. Pretend this is a week or so from now. And do it. What's our oxygen going to be? Always going to be -2. How many negatives do we have? 10. We have 2 nitrogens. Every nitrogen must be +5. Actually, I lied. There is one more. But that was so much fun. Let's do this one too. This is chlorate, so this is called chlorous acid. What are your oxygens going to be? -2. A hydrogen is bonded to an oxygen. What's it going to be? +1. That means we have how many negatives? And how many positives? So chlorine must be +5. All right. Well, I apologize for the difficulty in getting things going this morning. Remember, the quiz for balancing equation is on Blackboard right now. It'll be up until 11:30 tonight. Okay? It won't take you long. You get 2 attempts. Simple balancing equations. Make sure you enter 1 if the coefficient is 1. Oh, thank you for saying that. And on Wednesday, we do not have to come in for lab. I will email you the sheet.